Let's think about the slope of a tangent line for this function, f of x equals x squared plus 2, at two different x values. So at x equals minus 1 and also at x equals minus 2. So remember, we named the this operation that tells us the slope of the tangent line, we named that the derivative. So this would, what we're talking about here is the derivative at x equals minus 1 and the derivative at x equals 2, like this. Oops, I need a prime here. There we go. So at x equals minus 1, this is going to be, just by definition, it's the limit as h goes to 0 of f of minus 1 plus h minus f of minus 1 all over h. And we could calculate what this is, right? This is the limit as h goes to 0 of, let's see, f of 1 minus h. That's going to be, right, we need to plug minus 1 plus h, not 1 minus h. We need to plug minus 1 plus h into our function here. So minus 1 plus h squared plus 2 minus f of minus 1, and that's going to be 3, it looks like. Okay, all over h. And then do this whole calculation. So we're taking the limit of, as h goes to 0, of, let's see, there's going to be a minus 1 squared, so 1, and then minus 2h plus h squared plus 2 minus 3 all over h. And then we can simplify all this stuff as usual. So let's see, the 2, so 1 plus 2 is 3, minus 3, those all cancel. And now we have a common factor of h in the denominator and numerator, so we can cancel a factor of h. And then take the limit as h goes to 0, right? The remaining stuff here is a polynomial in h, so we can plug in h equals 0 to get the limit, because polynomials are continuous, and we just get minus 2. Okay, fair enough. And sure enough, it looks like at minus 1, the slope of the tangent line does have, it looks like it is about minus 2. All right, for the derivative at 2, well, this is going to be the, let me move down a little. This is the limit as h goes to 0 of f of 2 plus h minus f of 2 over h. So the limit as h goes to 0 of, let's see, f of 2 plus h. So again, we need to square 2 plus h. So that's 4 plus 4h plus h squared, and then plus 2, this 2 here, minus f of 2, which looks like f of 2 is going to be 2 squared is 4 plus 2 is 6, all over h. And then when we do the algebra to simplify, well, let's see, 4 plus 2, that's 6, minus 6, so those all cancel. Now everything in the numerator has a common factor of h with the h in the denominator, so we can cancel a factor of h. The remaining stuff is a polynomial in h, and polynomials are continuous at 0 in particular. So we can just plug in 0, and we get 4. And sure enough, it looks like the slope here is about 4, right? Tangent slope, about like that. Well, when I look back at these two calculations, it seems pretty clear to me that I basically did the same thing twice, right? The exact same algebra. The only difference in these two calculations are right here, it's a minus 1, and right here, it's a 2, right? So as I did this calculation, everything came from just those numbers being different. So what I could do, if I wanted to now find the derivative of f at different x values, I'd have to do this whole calculation again. Well, it seems silly to do this calculation over and over again when the only thing that's changing is the number that shows up right there. Whenever that happens, whenever you're doing a calculation over and over again, that's a sign that you should probably, instead of doing the calculation over and over again, you should do it one more time, but instead of having a number in this position, have a variable. When we do that, right? When we write this limit as h goes to 0 of f of, so when we have a variable in this spot, this value that we put here is an x value, so I guess we should write x minus f of x all over h. Well, this is a derivative, but what x value is this the derivative at? Well, it looks like it's the derivative at x, so we should write this f prime of x. What this is showing us is that this derivative, it's not just a single value, it's actually a function, right? If we can calculate this limit, then we'll have a formula for the function that tells us the tangent slope at any x value. Then if we want to ask about several different x values, we can just plug those x values into the formula that we get. So the change of perspective here is that this derivative, it's not just a number for a single x value, it's actually a function that describes many different tangent lines all at once. You just need to plug in the x value for the tangent line you want to know about. So actually calculating this limit is going to be a little tricky because we're taking a limit as h goes to 0, but also there are x's floating around. So when we calculate this limit, we have to be really careful because h is the thing that's going to 0, and as far as this limit is concerned, x is acting like a constant, right? When this limit is doing its job, x isn't changing. We can change x after the fact, but as this limit is letting h go to 0, x itself isn't changing. So how would we calculate something like this? Well, let's see. I guess we'll do what we always have done, right? Just take this, x plus h, and plug it into the definition of the function. So x plus h squared plus 2 minus f of x. F of x is x squared plus 2, and then divide this by h. Now we're going to have to simplify this mess. But, you know, just like the last two times we found derivatives for this function, the algebra is the same. Just multiply everything out and combine like terms. So when we square x plus h, we get x squared plus 2xh plus h squared plus 2. And now we can distribute this minus sign. So minus x squared minus 2. And now we can start simplifying things. Well, here's an x squared. There's a minus x squared. Those cancel. Here's a plus 2. There's a minus 2. Those cancel. And everything is over h here. So we get the limit as h goes to 0 of 2xh plus h squared all over h. Now this has a common factor of h in the numerator and denominator, so we can cancel a factor of h. This leaves us with the limit as h goes to 0 of 2x plus h. Okay, but this is a polynomial in h, so it's continuous at 0. We can just plug in 0. We get this term goes away. This term, remember 2x, that's acting like a constant as h goes to 0. And so the limit of 2x as h goes to 0 is just 2x. So this is our formula for the derivative of f at x. So you can see now that the derivative is actually a function. Here's the formula for the function. And this is the function that tells you the slope of the tangent line at any x value. You just have to plug in the x value you're interested in. And sure enough, if we take this formula and plug in minus 1, we get minus 2, which is the value for the derivative that we found earlier. And if we plug in 2, we get 4. And yes, that is the value for f prime of 2 that we found earlier. So this phenomenon happens, of course, not just for this particular function f, but for any function. So in general, we'll say that the derivative of a function is another function, and we're going to write it f prime of x, or this other notation, which I'll explain in a second. And the derivative is defined by the same derivative formula, except for instead of a particular x value, we just have this variable x plugged into our derivative formula. Okay, so this is one notation that we'll use for the derivative, and this is read f prime of x. The other notation, this this notation is inspired mostly by Newton, right? Newton and Leibniz sort of invented calculus more or less simultaneously. At least they didn't know about each other's work. And both of their notation has survived. So this prime notation is more of a Newton-style kind of thing. But Leibniz used different notation, and this is Leibniz notation. And it has some advantages. So the idea here is, the idea with this notation is, right, the derivative is a limit as h goes to 0 of delta f over delta x. So this notation is, the idea with this notation is just that, well, delta f and delta x both get infinitely small, and Leibniz used d of something to express the idea of an infinitely small piece of that thing. So df over dx is the ratio of an infinitely small change in f and to an infinitely small change in x. So you do have to keep in mind that df dx, this is a function. So to express the idea of evaluating this function at a value, at an x value, you can do one of two things. You can either just put parentheses next to it like usual. So if you wanted to evaluate this derivative at 1, you could just put a 1 right there. But a more standard way to do it, a more standard way to express the idea of evaluating this function is with a big vertical bar to its right, and then you write down the x value that you want right there. So if you're going to use Newton notation, that's just a prime, and then you put the x value in parentheses. And if you're going to use Leibniz notation, that's this ratio df dx. And then if you want to plug something into this function, you put a vertical bar and then the x value that you want. Something that's a little funny about this Leibniz notation is, at least for right now, it looks like this is a fraction, but this is not a fraction. It's actually a limit, right? The thing inside the limit happens to be a fraction, but this expression itself, df dx, isn't a fraction, it's a limit. So in particular, we can't treat this like a fraction. We can't separate it into two pieces, right? df doesn't mean anything on its own, really. dx doesn't mean anything on its own. Really, they only mean something when they are in a ratio. Now, that is something that we'll have more to say about later, but at least for now, treat this df dx as one big symbol, and it's the derivative. One nice advantage of Leibniz notation is it tells you what the variable is. And when you have lots of variables floating around, that is a very handy thing to express explicitly, what the variable is. So I will kind of switch back and forth between the two styles of notation just so that you get used to them. But personally, I find Leibniz notation better for various reasons that I won't get into right now.